So good morning, my dear students. Just we're going to continue with the things what we left in the morning class. So tomorrow morning class we discuss certain definitions of the terms which are used in the tolerance analysis, just like mean, variance, skewness, kurtosis, and even process capability. Right. So let us continue with the same thing what we left out in the morning class. So we were just discussing the process capability. We discussed what is process capability and what is the definition of process capability. Everything we discussed. So now let us continue with some more concept with the process capability, and we will going to complete that. Right. So is it the slide visible for everybody?
Yes, sir.
Yeah. Yeah. Now, in the morning class, we were discussing what is process capability. We discussed what is the use of the process capability study. So, where we discussed the process capability as a machine or a process can be defined as a minimum tolerance to which a machine can possibly be expected to work and produce no defective under specified conditions. Now, the question is how we can measure this process capability, right? So we'll say it is a qualitative one, it's quantitative one because we cannot do qualitatively. So quantitatively, how we can measure the process capability. So this process capability can be measured or it can have the quantitatively by parameters called process capability indexes. Okay, so the process capability can be measured statistically and it can be expressed by using the process capability index CP, CPK, CPU, and CPL. Okay, where CP corresponds to the good measure when process is centered in the middle of USL and LSL. So we will going to discuss one by one what is CP and what is CPS, what is CPK, and all those things, right? So statistical measure or way of measuring the process capability is expressed in terms of the process capability indexes. These are all called process capability indexes: CP, CPK, CPU, CPL. Okay, and where CP we say it has a good measure when the process is centered in the middle of USL and LSL. That's all what we discussed in the previous one. So this is the one what we have. This is a CP value which is more capable, very capable process, what we call it as, right? So now let us take what is CP. CP, how do we calculate? CP is calculated as the ratio of USL minus LSL divided by 6 sigma. So 6 sigma means it is 6 times. It is the standard deviation. Okay, standard deviation there. So here, what we do is, so measuring the process capability. So here we going to have here we will going to have the value of CP. The value of CP is calculated as a difference between USL minus LSL divided by 6 sigma. So this is the one process capability index which is used to measure the process capability statistically, where 6 sigma is 6 times the shorter term sample standard deviation of the production. So 6 times the short term sample standard deviation. So I think this we'll go to discuss later when we solve the problems also, right? The next term is CPU. So CPU is used when we process that have only USL, means only upper specification limits are there, when there is no lower specification limits. So there are certain processes where only upper specifications will be given, just like the tolerances. So tolerances can be, it might be unilateral tolerance, or it might be bilateral tolerances. So unilateral means only on the one side, either on the positive side or on the negative side. So when it comes to the bilateral tolerances, you can give the tolerances on both the sides, either on both positive as well as the negative side. But sometimes there are some processes where you will need to have only the upper specification limits and there is no lower specification limits. So in such cases, we use the process capability index in terms of CPU. U corresponds to an upper specification limit. So this is the process capability index used only when the process have only USL, that is upper specification limit. So CPU is equal to USL minus mean X bar divided by 3 sigma. So these are all the formula for calculating the process capability index depending upon whether it is a CP or CPU or CPL or CPK. Got it? So CP is USL minus LSL divided by 6 sigma, whereas CPU used only when there is only USL, where CPU is equal to USL minus X bar corresponds to the mean divided by 3 sigma. Next comes CPL. So this CPL is used for the process that have only LSL. LSL means lower specification limit. So if we have the specification limits on the lower side, then we will going to use the process capability index in the form of CPL, C suffix PL, where CPL is equal to X bar minus LSL divided by 3 sigma. Okay, so where X bar is the arithmetic mean value. Okay, so now CPK is a good measure when the process is not exactly centered. When the process is not exactly centered, okay, then we go for a process capability index in terms of CPK, okay, where CPK is minimum of these two values. So CPU and CPL, you have to calculate both, and if the process is not exactly centered, then we go for CPK, and which can be taken as minimum of these two. Whichever the value you will going to get minimum value, that will be considered as the CPK value. Please remember all these things. So CP, when it is exactly centered, so it can be calculated by using the USL minus LSL by 6 sigma, whereas CPU, the only a USL is been specified, so which is USL minus 6 sigma, sorry, USL minus X bar divided by 3 sigma, whereas CPL is the process capability index when you have only LSL is specified, so which can be calculated as X bar minus LSL divided by 3 sigma, and CPK. CPK is a very good measure when the process is not centered, exactly centered. Okay, so where you are going to get the minimum of the two values, that is CPU and CPL. Minimum of CPU and CPL will going to be used as the measure of CPK. Got it? So this is how we just measure the different process capability indexes. Now, interpreting the process capability indexes. So whenever the values are there, how we can interpret the process capabilities. So let us take one by one over here. When the CP has a value of 1 or greater, when the CP has a value of 1 or a greater, the process is producing a product capable of meeting specifications. When the CP value is 1 and more than 1. Okay, so when the value of CP is having value more than 1 or 1, then we will say the process is producing the product capable of meeting specifications. Means the process can meet the specifications what they have given. The CP value does not reflect process centering. So it does not show whether the process is centered or not. When the process is centered, CP is equal to CPK. So that's what we told in the previous slide. CPK value is possible when it is not centered properly, when it is not exactly centered. So the process will go into process index, the process capability index what we use is a CPK. So when the process is centered, the value of Cp will be equal to Cpk. Cpk value is always less than or equal to Cp. In the sense, so the process capability index is not exactly centered. So we use Cpk. So the value of Cpk is always less than or equal to Cp, and it cannot be more than Cp. When the Cp is greater than or equal to 1 and Cpk has value of 1 or more, it indicates that process is producing product that conforms to the specifications. So that's what the first one, the point one, what it specifies, it is equal to 1 or greater than 1, and value of Cpk is 1 or more. It indicates that the process is producing product that conforms to the specification. When the Cp value is less than 1, it indicates that process is producing the product that does not conform to the specifications. In the sense, the Cpk value should be either equal to 1 or it should be greater than 1. It should not be less than 1. If it is equal to 1 or more, so that is what it is indicating, that process is producing the products that conforms to the specifications. In the sense, the products are produced within the specification limits. If the value of Cpk is less than 1, then it indicates that process is producing product that does not conform to the specifications. A Cp value of less than 1 indicates that process is not capable. So this is very important. The process capability index Cp value, if it get the value is less than 1, then it is showing that the process is not capable. And if Cpk value of 0 indicates that process average is equal to one of the specification limits. So be careful. See, when you are calculating Cp and Cpk value, whenever you get the value is equal to 0, what does it indicate is the process average is equal to one of the specification limits. Then a negative Cpk value indicates that average is outside the specification limits. So means, yeah, negative of Cpk value indicates that average is outside the specification limit. So in a sense, when you are interpreting the process capability indexes, in the sense of the value of process capability indexes can be interpreted by taking all these things. So whenever you want to have the process is capable enough, the Cp value should be greater than 1 or it should be equal to 1. If it is less than 1, it is confirms that the process is not producing the products which will conforms to the specifications. So this is how we start what we call it as interpreting the process capability indices. This is regarding the process capability, very, very, very important from the examination point of view, and even understanding the process capability indices. Okay. Yeah. Any clarification, my dear students, at this point? When your clarification, let me clarify and let me move to the next slide. Anybody having any clarification?
No, sir.
Right. So till now, I am talking about the terms which we generally use it for understanding the concept of tolerance analysis. I think you have studied what is tolerance in your engineering metrology when you studied in your UG level. Anybody can define what is tolerance? Anybody can define what is tolerance? Yeah.
Difference between upper limit and lower limit.
Difference between? Hello?
Upper limit and lower limit.
Upper limit and lower limit. Okay. Yeah. Anything? Anybody can give much more well-defined definition of tolerance?
Permissible limit.
Permissible limit. Okay. Okay, I will put it in different way. Why the tolerance is required? Is it necessary to give tolerance to the products?
Yes, sir.
Huh?
Yes.
Yes, sir.
Why? What is the necessity of providing tolerances? Anybody can answer.
In order to ensure proper fitting between the two parts.
Proper fitting between the two parts. Okay. Right. Next. Anybody?
Variation in the physical dimension.
Variation in the physical dimension. Okay. Why this variation happens?
Due to thermal.
It might be due to temperature difference also, sir.
Sorry?
Thermal.
Might be due to the temperature also.
Temperature also. No. Why that variation in the dimensions will take place? That's my question.
Sir, it's because while manufacturing, there will be a small difference in variation of those measurements, sir.
No, that's I agree. I'm saying why that variation happens. My question is definitely there will be some difference. I agree, but why that difference will come? Why that variation will comes? What is the reasons for variation that is taking place in the dimensions of the components? If I want to manufacture a shaft which is having a diameter of 20.5 millimeter, so I want to produce around 50 such shafts of same size, and I am using the same machine, same operator. Is it possible that all the 50 shafts will measure 20.5 exactly?
No, sir.
No, sir.
Why? Why it is variation? You can see same operator, same machine, same dimension, same
Sir,
material.
maybe there will be error in the machine, sir. Small, minute errors will be there, or wear and
Okay.
tear tool will happen.
Okay. Okay. So problem with the machine. Okay. Next.
To overcome those problems, we use tolerance.
No. That's we will come to that later. I will come to that later. Overcome that variation, we will provide tolerance. Right. Now my question is, let me complete that. Why that variation happens? That's my question. So one is some problem, maybe some difference will be there in the machine, right? That's agree. I will agree. Next, what will be the other? Sorry,
Human error.
human error. But then
Environment. Effects.
environment. Okay. Then what else? What else makes the difference in the dimensions?
Even the wear and tear of the material.
Yeah, the material itself. Material itself. So if it is a defective, definitely you will going to find out. You're going to experience the variation in the dimension. So generally, that's what we call it as three M's: man, machine, and material. All these three will contribute for the variation in the dimension, whether it is a man, of course. So is what we call it as physical and psychological conditions of the man. The same person may be different at one point and maybe different behaving in a different point. So the human error, that is what we call it as the psychological effects. So human and physical and psychological effects will also affect over the changes in the dimension. That is the one part. Second part, man machine. So machine will have its inherent problems. So maybe that's what the tool wear out and tear out. So definitely that will also contribute for the variation in the dimension. And the third one is the material. If the material itself it is having some defects, then that will also contribute for the variations in the dimensions. So why I'm talking about this point at this stage is, so of course it's not possible to produce the same kind of ideal kind of products. So one product, one component will differs from other component, even if everything is gold good. So it is only possible with a God who can make all identical items. Apart from God, nobody can do the identical parts. So the main reason for that is contributing from man, machine, and the material. So there will be some inherent changes that will be going to take place, and these variations will be contributing for the changes in the dimensions of the product. So that is a reason why some amount of variation should be permissible. It should be permitted. So it's not that if it is 20.5 exactly, it is not possible for us to manufacture a shaft having the same dimension. All 50, it is not possible. So some may get 20.49, some shaft may get 20.51. So like that, the dimensions may going to be varied across the exact value. Exact value is 20.5 means you may get some shaft measuring 20.49, some shaft measuring 20.51. So this amount of variation should be permitted to undergo in the dimensions because of the effects from the man, machine, and the material. That permissible variations in the dimensions, we call it as a tolerance. So we call it as a dimensional tolerances. In the sense, we are permitting the dimension to vary from its nominal or a base value up or below. So means above or below. So the above value we call it as an upper limit, and the lower value we call it as a lower limit. So that variation between the upper and the lower limit will be constituted as a tolerance for us. Right. So that's based upon that only you will going to get a unilateral tolerance or a bilateral tolerance if the variation is permitted only on the one side, whether on the positive side or on the negative side, it will constitute it as a unilateral tolerance. And if the variation is permitted on the either side, on positive or negative side, then that will be called as a bilateral tolerances. So this is what you might have studied in your engineering metrology, and you know how to calculate these tolerances, and based upon the tolerances, how we can define a fit. So clearance fit, interference fit, or transition fit, all those things, right? So why I have taken this topic at this junction here is, so you have studied the dimensional tolerances, and also I think you might have been very minutely you might have been exposed for another type of tolerance, what we call it as geometric tolerances. See, you are talking about only with respect to the dimension, but when it comes to the geometry, see, it is not that the variation takes place only with respect to the dimension. The variation can also takes place with respect to the shape. We are talking with respect to the size. The variation can also happen with respect to the shape also. So if the shape varies, then the product cannot be assembled. You can manufacture, but it cannot be assembled. Simple example: if you want to get a ovality in the cylinder, or if you get a ovality in the gear, or if you get a ovality in the shaft, I think you can understand what is ovality. Am I right? Can understand what is ovality?
Yes.
Hello. Can you understand what is ovality? What do you mean by ovality? Hello.
Sorry.
Now, what do you mean by ovality?
Sir, it's a degree of variation from the perfect circle, sir.
Yes, it's not exactly a circular. not exactly circular, in the sense its radius does not remain constant. So if you find such kind of problem, so this kind of problems you will going to experiences when you are assembling a product. So you don't find these things in your manufacturing an individual component. So individual component, you will say the measure this is a radius, this is a diameter, we'll go on to take and we're going to put it. But when you start assembling this component with respect to the another one, simple example, I was talking a bearing and a shaft, or a gear and a shaft. So both should be having the same shape. Shape should be a circular. Both have a circular shape. Then the bearing or the shaft can fit in the bearing, or gear can be mounted over the shaft, or a pulley can be mounted over the shaft. If you find any kind of ovality, in the sense either a shaft or in the case of a gear or in the bearing, then you cannot fit the shaft inside the bearing, or you cannot mount the gear over the shaft. So we are talking about only the variation with respect to the size, but with respect to the shape, it is also very important thing for us. So if you find any variations in the shape, so definitely it will also constitute for the difficulty in the assembling the components. So therefore, so we need to permit, so we need to allow, or we need to undergo as some amount of variation in the form or the shape of the component, and that permissible variation we term it as a permissible variation in the size is a dimensional tolerance. Permissible variation in the shape or the form, what we call it as, we call that as the geometric tolerance. So why I have taken these things means we have to discuss the concept of geometric tolerance now. Okay, so geometric tolerance is nothing but it is the variation in the size or variation in the shape or the form of a product. So this is what we call it as geometric tolerance. So you can see the slide over here, a geometric tolerance. A geometric tolerance is the maximum or minimum variation from true geometric form or position that may be permitted in the manufacture. Okay, so of course maximum or minimum variation is possible, so that can be permitted in the manufacture. Geometric tolerance should be employed only for those requirements of a part critical to its functioning or interchangeability. So this is very important again. See what happens. So geometric tolerances are employed only for those requirements of the part critical to its functioning. That's what I was talking about. So a piston and a cylinder, simple example. Piston and a cylinder, again it is a hole and a shaft again, right? So piston should sit inside the cylinder. So if there is some ovality you have experiences either across the surface of the piston or the cylinder, so you cannot have a what we call it as a required allowance, so that the piston can reciprocate inside the cylinder. So if it could not do that, then it cannot function satisfactorily or as per the requirement. So this is where the geometric tolerances will come into the picture. So wherever we find an interchangeability, I think you might have studied interchangeability and selective assembly in your again metrology concept. So interchangeability concept will come into the picture. The geometric tolerances are very, very, very important for us. Okay, so therefore geometric tolerances should be employed only for those requirements of a part critical to its functioning or interchangeability, right? So I will just read out the geometric tolerance is the maximum or minimum variation from true geometric form or position that may be permitted in the manufacture. Got it? So now let us look at the different symbols and characteristics of the geometric tolerances. There are 14 geometric characteristic symbols. They are categorized with the type of geometric control, form, profile, orientation, location runout. So this is the major classification: form, profile, orientation, location runout. So of course the category, these symbols are represented over here. I think this you might have studied in your metrology concept also. Same thing might be it has been repeating over here. So but it in a different way we will going to discuss this, right? So here under the category of form, we have a straightness, flatness, circularity, and cylindricity. Under a profile, so we have a profile of a line, profile of a surface. Under orientation, we have an angularity, perpendicularity, parallelism. Location, we have position, concentricity, symmetry. And under runout, we have circular runout and total runout. This is the 14 geometric characteristic symbols. This is very important because definitely one question will be there on geometric tolerances. Write a short notes on geometric tolerances and their symbols. So it carries 8 to 10 marks in your exam. Okay. So you need to know the form, profile, orientation, location, and runout. So these are the 5 different categories they have made. So under which are those comes and what are those things, what are those symbols, we're going to discuss in detail one by one, right? The form tolerance. Yeah. So first one under the form tolerance is a straightness. The straightness requirement specifies how perfectly straight a target should be. It is applied to the lines and not planes. So remember, straightness is applied to the lines only, not for the planes. Okay, and it represents a curve in the center line or a generatrix. Therefore, the straightness is used to indicate the warpage tolerance of long objects. See, look at here how it should be. The straightness. See how it is be represented. See. Straight, the symbol is used as a line. Line is a symbol used for a straightness. So this is should be in straight line. This surface should be straight, and it is of course this is 0.1 millimeter less what they will see. This line and this line should be 0.1 millimeter or less when straight. So this is the indication of a straightness geometric symbol. Okay, be careful when you are writing the symbols and understanding the what is the significance of those symbols. This is a straightness. Second comes flatness. The flatness requirement specifies the evenness of a surface or how accurately flat the target plane should be. The most protruding part and the most concave part must be at the specific distance between the two planes that are separated vertically. See, the flatness is being represented by this symbol. Look at this parallelogram. Just like a parallelogram, this is the indication, the symbol which indicates the flatness. So how do you say the flatness in the sense? So see, this is a symbol, the representation of a symbol in your drawing sheet. So how the geometric tolerance will be given? The symbol followed by their numerical value. Okay. So the most protruding part and the most concave part must be at a specific distance between the two planes that are separated vertically. So the distance should be given like this. So they are flat. So from the flat, the concave part or protruding part should be, so what, how much it should be shown. Then the third one is the roundness. The roundness requirement specifies how perfectly circular a target, the circular cross section of a shaft, bore, or a cone should be. So this is the third one. The roundness symbol is a circle. Okay, the roundness requirement specifies how perfectly the circular a target, the circular cross sections are. Okay, so again you will have the allowances. 0.1 millimeter is allowable, right? Shaft, or in the case of a bore or a cone, or what it should be. Next comes cylindricity. The cylindricity specifies how accurately circular and straight a target cylinder is. Straight or a circular. Straight and circular, it is very important, cylindricity. So the cylindricity is been represented by this symbol. So just remember these symbols. So how cylindricity will be expressed or it has been symbolized. Cylindricity requirement means how accurately circular and straight a target cylinder is. The value represents any distortion in a cylinder. So is there any changes if you experiences? So then you will going to get this kind of experience. This is a cylindricity of the geometric tolerance. This is all the four or corresponds to the form. Next comes the profile tolerances. So the profile tolerance of a line. So how do you express the profile tolerance of a line? The profile of the line requirement indicates whether the curvature of a design part is made to its design. The value indicates any distortion in the profile line. So whatever the value you can see here, so it has been showing, so this much amount of distortion has been taken place in the profile of a line. Okay, the line element that appears on the cross section of the surface. The cross section line cutting across specified curvature must be within the tolerance zone. So how much means you can go up to the surface can undergo a distortion up to 0.03. 0.03. Okay, so this is the permissible limit for the profile of the line, how much it can go. Okay, next comes profile tolerance of a plane. The profile of the plane requirement indicates whether the curvature of a design part is made to its design. Unlike the profile tolerance of a line, the profile tolerance of a plane involves the entire specified curvature. See, this is the profile tolerance of a plane. See here, this is a symbol which indicates the profile tolerance of a plane, and it indicates whether the curvature of a design part is made to its design. The curvature part, look at here, the curvature has been made to its design or not. So if that is not there, how much it can be permitted, how much variation can be permitted, it is indicated in the block. See, it indicates 0.1 millimeter is allowable to undergo variation. The profile tolerance of a plane. Got it? The third one comes orientation tolerances. So under orientation tolerances, we have one is parallelism. When it appears to be similar to the flatness, parallelism involves a datum plane, a reference line. The parallelism requirement specifies that two lines or planes are parallel to each other. So this is a symbol which is used for parallel. Okay, so either the two lines or the two planes, whether they are parallel to each other or not, it has been shown by this symbol. So see here, so they will going to take a datum. A corresponds to the datum in this sketch. Okay. Yeah, A corresponds to the datum over here. With respect to this datum, the line is parallel. You need to be parallel, and the allowable variation is, or permissible variation is 0.05. 0.05. So this is the line, and of course in the same case the plane also. So plane, how you can make the thing 0.05 millimeter or less. This is what the parallelism. In the similar way, we have another one called perpendicularity. The perpendicularity requirement specifies the accuracy of how perpendicular a target is to be to the datum. So again, you have a datum. So whether that surface is how much perpendicular to it. So this is like this, and this is like this. So with respect to the datum, whether this line is perpendicular or not. So if not, how much is allowable? How much variation is allowable? This is 0.03 is the allowable variation in the perpendicularity. So this is a symbol. The perpendicularity symbol is this one what we generally use. Okay. Next comes angularity. So this is a symbol. Angle is a symbol what we use. The angularity requirement specifies how accurate an angle is to the data when the specified line or a plane is not 90 degrees. Instead of degrees, the millimeter is used as a unit for the value of angularity indication. Sometimes they are going to give it in the form of a value. So this is a datum. Okay. So A is the datum. With respect to A, what is this angle? Whether it is 45 degree or it is been variation. So 0.3 in the values, in the sense it will be the radians they will going to give it in the form of a radians, how it can be varied. So it is 0.3 millimeter or less. This is the permissible variation. Remember, permissible variation of an angle of a surface with respect to the datum. Okay, with respect to the reference plane or with respect to the datum, so that we will going to specify. This is what angularity, right? And the last one is location tolerances. See, location tolerances, sorry, fourth one, I'm sorry. Fourth one is a location tolerances. So where we have two true position. The true position requirement specifies the accuracy of the position in relation to the datum reference planes. True position, whether it is exactly, it has been positioned exactly there. Requirement specifies the accuracy of the position in relation to the datum. So with respect to the datum, so if you say A is the datum and B is the datum, these two are the datum surfaces for you. With respect to these two, whether this hole has been centered exactly at this point or not. So what is exactly it has been positioned, and if not, what is the allowances is can be given for the variation in the position. That is what we call it as a true position. So the symbol used is a true position. This is a symbol position what we use. Then the next one comes coaxiality. The coaxiality requirements specify the coaxiality of the axis of the two cylinders. No deviation in the central axis. So look at here. So this is the datum. Okay. And this is the line. So these two lines should be coaxial, means it should be parallel. It should be exactly along the same line. So there should not be any variation in this axis. See, this dotted line what we have got, and the line which is other continuous line. See, look at this. The coaxial. So this is 0.03. 0.03 millimeter is permissible variation in the coaxiality or in the axiality. Next comes concentricity. So it is represented with a circle within a circle. The concentricity requirement specifies the accuracy of concentricity of the axis of the two cylinders. No deviation of the cylinder center. No deviation of the center. So when the two cylinders have been placed one over one within another one, so the center, the axis of the two cylinders should coincide. There should not be any deviation in the center of the axis of the cylinders. Unlike coaxiality, the datum is the center point for the plane. So A will represent the center point for the plane. So cylinder, this is how we are going to indicate the representation of a concentricity geometric tolerance. And the last one in this here is symmetry. The symmetry requirement specifies the accuracy of how symmetrical a target is to the data. So it's symmetrical in the sense these two. Okay, so with respect to this axis, so whether these two lines are symmetrical or not, this is very important for. So that symmetricity is given by a datum. This is a datum surface, and allowable variation in the datum surface is a symmetricity is 0.05. The symbol which we use it for symmetricity is this one, right? Then the last one is runout tolerance. The runout tolerance is of two types. One is circular runout and total runout. In the case of a circular runout, specifies the runout of any part of a circumference when a part is rotated. To meet the circular runout requirement, the runout of the measured value when the part is rotated must be within the specified range. So this is when you just rotate. When you rotate the circumference of any part, so you will going to find there will be some amount of runout. In the sense, there will be variation in the diameter or variation in the length, whatever you might want to make. So that runout will be expressed by an arrow. So that permissible value will be given as a diameter 0.03. So when you write to see, this is what the runout, what we call it as. This is circular runout. In the similar way, we have total runout, so which specifies the runout of the entire surface of the part when it is rotated. So circular runout, only the circumference. When it comes to the total runout, so entire surface rotated, to meet the runout requirement, the runout of the measured value of the entire cylinder surface must be within the specified range. So entire surface, you look at here how it is happening. So here only this circular was what we have run out. So if we take this total part, so the dial indicator will be there to measure the runouts. So when you pass a run, what we call it as the dial indicator over the surface, so it should read 0 from one end to the other one end. If any changes, if any deviation or if any deflection you can find out in the pointer, that is indicating that so the runout has been occurred. So if it takes place only across circumference, so that will constitute a circular runout. And if you do it for the entire surface or entire product, entire surface, then it will become a total runout. So the symbol what we use it for total runout is this one. Okay, so these are the 5 different types of geometric tolerances. So we'll continue this in the next class. So cumulative effect of tolerances in the next class. At that point, I will stop you. So if you have any clarification, you can have. Otherwise, we'll go for a quiz.
Okay.
Yeah. Right. So let us move on to the quiz over there. Yeah, so you can answer the quiz. Another 10 minutes left out. After answering the quiz, submitting the paper, you can leave. No problem. We will discuss next things in the next class.
Sir, how to answer the cylinder blanks?
Type there.
Should I write the complete definition, sir?
Not required. Only those 2 words. That's enough.
But also it will show not correct, sir.
No problem. That I have not assigned the correct answer for that. You just type it. No problem. I not type the answer for that. I will just correct it later. No problem.
Hello, sir.
Yeah, tell me.
Sir, due to network issue, I'm not able to attend the test, sir. I have network
What's
issue at
happening?
my home, sir. The link is not at all opening, sir.
Okay, okay, man. Leave it. Nothing to worry. Don't worry. So after submit your quiz, you can leave, no problem. Next class, next week, we will want to discuss the remaining. Please submit it and leave.